CA2 Unit 1 Topic 1 is on lattice enthalpy. This is the specification for the topic. This topic uses information that you will have found in earlier AS modules, in particular the enthalpy topic. It is important that you understand exo and endothermic reactions, the standard enthalpy of formation and combustion, bond enthalpies, and the idea of Hess's law. It is also important at this stage that you understand what an ionic lattice is composed of, that there are both positive ions and negative ions in a regular arrangement. These are the new definitions that we will meet in this topic. However, we will meet definitions that we met at AS level. The first set of definitions from AS level were our ionization energies, which we met in Unit 1. And then in our enthalpy topic in Unit 2, where we looked at enthalpies of formation and standard enthalpy changes and also Hess's law. Before we look at the definitions, let's just recap on standard conditions. Standard conditions are considered to be a temperature of 298 Kelvin, 100 kilopascals pressure, any solutions in a concentration of 1 mole per decimeter cubed, and all substances are in their standard states. Let's look at our first new definition, which is standard lattice enthalpy. The standard lattice enthalpy is enthalpy change when 1 mole of an ionic compound is converted into its gaseous ions under standard conditions. This value will always be positive, so it is an endothermic process. This is an endothermic process since energy is needed to overcome the attractive forces between the ions and separate them. Ionic compounds are generally solids. The other definitions you will need to know are the standard enthalpy of formation, which you met at AS level, the standard enthalpy of atomization, which is when 1 mole of gaseous atoms is formed from the element in its standard state, and the standard bond dissociation enthalpy. By definition, enthalpy of atomization produces 1 mole of gaseous atoms, so you have to watch out for diatomic elements such as chlorine. So half a chlorine molecule would give you 1 chlorine atom. However, that means you need to use half a mole of chlorine molecules to get 1 mole of chlorine atoms. Sometimes you will find you will be given bond dissociation enthalpy values instead, and that is where you will break the chlorine-chlorine bond in the molecule and produce 2 chlorine atoms. What you can see is the bond dissociation enthalpy is twice the standard enthalpy of atomization. It's really important when we do calculations that you watch what value you have been given. We met first and second ionization energies at AS level. How will they compare? They are both endothermic values as we are trying to remove electrons, but we will find that the second ionization value will be much higher than the first, as an electron is being removed from a positively charged ion. Sometimes we will find in calculations a value will be given for both the first and second ionization energy added together. We are going to meet first and second electron affinity in this topic, and this is the enthalpy change when 1 mole of gaseous atoms is converted into gaseous ions with a single negative charge and then with a double negative charge. This time, if we compare how the value of the electron affinities compare, the first electron affinity is an exothermic process, but the second electron affinity is an endothermic process, as energy has to be put in to add an electron to an already negatively charged ion. Now that we've met the different enthalpy changes, you will have seen that some of them are exothermic processes and some are endothermic processes. It is important that you learn these. Lattice energy cannot be found by experiment, and so is calculated using a Bohr-Haber cycle, which uses other quantities which can be found experimentally. A Bohr-Haber cycle is just an application of Hess's cycle where we use an alternative route. In the simple cycle below, the delta H represents all the enthalpy changes needed to change sodium in the solid state and the chlorine gas molecules into sodium and chloride ions in the gaseous state. A Born-Haber cycle includes all of these enthalpy changes. We're now going to look at how we draw a Born-Haber cycle. This is how we will usually see a Born-Haber cycle. We will write the formula and equations on the horizontal lines. We will write the energy changes along the arrows. Endothermic values will have the arrows pointing up. Exothermic values, the arrows will point down, and the size of the arrows give an indication of the comparative enthalpy values. Let's look at how we construct a Born-Haber cycle. The first line we draw is for the elements in their standard states. The first arrow goes down. It represents an exothermic process, which is the enthalpy of formation of sodium chloride. What we're going to do now is we're going to go in an alternative route to make sodium chloride. The first thing we are going to do is take our sodium and we're going to atomize it. This is an endothermic process, so the arrow is pointing up. After we atomize our sodium, we are going to ionize it, and again the arrow is pointing up because this is an endothermic process. Now let's look at chlorine. We are going to atomize our chlorine to produce chlorine atoms, and then we are going to add an electron to the chlorine atoms. Once we add the electron to the chlorine atom, we have formed a chloride ion. This is the electron affinity of chlorine and is an exothermic process, so the arrow is going down. The final stage is where we put in our arrow for lattice enthalpy, and that is where we start with the sodium chloride in the solid state and we put in energy to form the sodium and the chloride ions in the gaseous state. Our Born-Haber cycle is now complete. We can use this Born-Haber cycle to find any unknown value. Let's use the Born-Haber cycle we have constructed to find the lattice enthalpy for sodium chloride. We have put in the numerical values for all the other processes onto the diagram. If we now apply Hess's law, we can say that the enthalpy of formation is going to be equal to the enthalpy of atomization of sodium plus the enthalpy of ionization of sodium plus the atomization of chlorine plus the electron affinity of chlorine minus the lattice enthalpy. We can then rearrange the equation to find the lattice enthalpy. If we now slot in all the values, you can see that the lattice enthalpy for sodium chloride can be calculated as positive 776 kilojoules per mole. The specification asks us to construct Born-Haber cycles and associated calculations for halides and oxides of group 1 and group 2. We now should be familiar with the Born-Haber cycle for sodium chloride. Sodium chloride is a group 1 metal with a group 7 halide. If we have a look at this Born-Haber cycle, we can construct an equation that will allow us to find out an unknown value. If we are asked for the lattice enthalpy, we can rearrange this equation to give the value for lattice enthalpy. Let's now look at other Born-Haber cycles. The next one we're going to look at is magnesium chloride, which is a group 2 metal and a halide. So what is different in this Born-Haber than the sodium chloride Born-Haber cycle? The first thing you will notice is that because it's magnesium, you're going to have a first and a second ionization energy required to form the magnesium 2+ ion. As you need 2 chlorides, you're going to start with chlorine gas. So you'll either need 2 enthalpies of atomization of chlorine or the bond dissociation enthalpy of the chlorine molecule. Because you have 2 chlorine atoms that need to form ions, you will need to multiply the electron affinity for chlorine by 2. This means our equation will be slightly different, as we will have the first and second ionization energy of magnesium, and we will need to use 2 atomization energies of chlorine or the bond dissociation enthalpy of the chlorine molecule, and we will need to add 2 electron affinities of chlorine. The next example we will look at would be calcium oxide, which is a group 2 metal with an oxide. In this case, the Born-Haber cycle will also have a first and second ionization energy of calcium to form the calcium 2+ ion. When we form the oxide ion, we need to add 2 electrons. So we will have the first electron affinity and the second electron affinity. Remember, the first electron affinity is an exothermic process, so the arrow is going down, and the second is endo, so the arrow is going up. Remember then, when you construct the equation, that you have your first ionization energy and second ionization energy of calcium, and you also have the first electron affinity of oxygen and the second. The final example is sodium oxide, which is a group 1 metal with an oxide. This time we will have the same first electron affinity of oxygen and the second electron affinity, but because we have 2 sodium atoms in the compound, we will need to take the atomization of sodium and multiply it by 2, and we will have to take the ionization energy of sodium and multiply it by 2. And these will also be found in the overall equation. Let's try and explain lattice enthalpy values. Lattice enthalpy values are always positive because lattice enthalpy is an endothermic process. If we look at sodium chloride and potassium chloride, we can see sodium chloride has a more positive, a more endothermic lattice enthalpy value than potassium chloride. The only difference between sodium chloride and potassium chloride is the size of the metal ion. The lattice enthalpy depends on the charge on the ions and the size of the ions. So in this case, the charge on the ions is the same. Smaller ions are more closely packed in the lattice and so are more attracted to each other. Ions with a high charge are more attracted to each other as well. So smaller ions will have a greater attraction for each other because they have a higher charge density. If we have a look at the following table, we can see which combination will give us the strongest ionic bonding. We'll be looking for a highly charged ion and a small ion. If we look at our metals, we can see that aluminium ions are the smallest, most highly charged ions. And if we look at our non-metals, we can see that the oxide is the smallest, most highly charged non-metal ion. Therefore, aluminium oxide has the strongest ionic bonding. Sometimes we are asked to explain the trend in lattice enthalpy values in terms of the Born-Haber cycle. If we have a look at this example where the only change is the metal ion changing from sodium to potassium to rubidium, you can see that the lattice enthalpy values become less exothermic. If you think of your Born-Haber cycle, because your non-metal ion remains the same, the only change will be the atomization and ionization of the metal ion. This would also be the same if we look at these examples where we are changing the non-metal ion. So in this case, it's only the bond dissociation and the electron affinity values that are changing, and they will result in an overall change in the lattice enthalpy value. Be prepared for other types of Born-Haber cycle. Remember, a Born-Haber cycle is a Hess cycle, so they may not always look the way we usually draw them. And this is an example from a past paper in 2012.